pretty good job on the quizzes. I graded them really, really quickly. So if you missed something that I graded as correct, then maybe check and study on your real picture of the graph. Because again, I was grading really quick. But Merry Christmas. So don't get good snow.
Yes. My parents played and my little brother plays, so I'm just there. Okay, but how did the snow melt? Like, it was
When I first touched it, I was like, what the heck is this? It's like,
Yeah.
it's like it just was so soft.
Yeah, it was a little weird. You're right.
It's right down there.
12 degrees outside.
All right, so can I just encourage you on this to really, really be honest with yourself and me? Every year I go over this, and every year people are like, yeah, I totally get this. And then I know that there's like 3 people in the room based on what I see from their test that they don't get it. They don't. For some reason, what I say, and I really try to say it some different ways, doesn't click. But here's the thing. If you're willing to come see me and go, I think I get it, but I keep missing the question, so I don't think I do. If you're honest with yourself, stuff down from Schoology, if you miss it, come see me. I can straighten you out with domain and range. It is a really big deal when it comes to AP Cal, Pre-Cal. It's not an overly difficult topic. Sometimes it can be difficult to find the domain and range, but not with what we're doing. With what we're doing today, it is very visual, okay? So as I'm going over it, again, don't just say to yourself, yeah, I think I get it, maybe, sort of. It's an easy way to lose or 2 on this test. And there's literally, it's right or wrong. There's no work to be seen except your answer. So it's not like I can go, oh, careless error. It'll be purely conceptual. And it's the easy questions. It'll be the easiest things on your test that I'm asking you to do is, what's the domain? And you write out the intervals. But it's new, and every year, out of a group of 40 people, there are 3 or 4 that don't get it and miss it all the way across the test. And it's to know that if you come and ask me, because I have had people come and ask me before that were clueless, and I worked with them enough that they're like, oh, and it just clicks. And once it clicks, you'll be fine. So hopefully it'll click initially, but be honest with me. Don't be embarrassed to ask questions. Please do that for your sake. You'll probably be a hero for somebody else in the class anyway. All right, domain. Most people mess up domain because when I say, what's the domain? If you're not reading, what would you say? I don't say that because that it very likely is not. But like, what's the definition of domain? Okay, people just say X values for domain, Y values for range. Now, that's kind of true, but what do you really mean by X values? Like if I say, what is the domain of a function? The X values that make it true. Now, what do I mean when I say make it true?
They give you a rational, like not imaginary.
What do you mean by answer?
For the
Y. So what we're saying, if it's in the domain, then the X values that when you plug them into your function give you actual Y values. Now we've had asymptotes on some of our graphs, right? Like the volcano graph had an asymptote. If I plug 0 into those functions that have an asymptote there, does that give me a Y value? No, it's fine there. You got like 1/0 or something. That's not in the domain. That would be an example of something not in the domain. But if anywhere else on that function, if I plug something in, am I going to get a Y value? Think about 1/x squared. No matter what I plug in there, other than 0, I'm going to get some Y value. Well, that's one way of thinking about domain, is looking at the graph and asking yourself, is there anything that would keep me from... Now, at the beginning of the year, we talked about domain. And I said that there were 2 places that you could get the trouble with domain based on what you knew then. Do you remember what those were? I've already mentioned one. Say again? Okay, square roots, not because if I plug in a 3, I get root 3, and that's just a little irrational. That's okay, right? I can go plug in a 3 and go up 1.7-ish. What's bad or root? I can't plug negatives in. Because when I plug negatives, I get imaginary numbers that are not it's a basic square root, but I can't go left. Are you with me? So in a situation like that, I couldn't plug any negatives in. What's another situation? Anytime I have a denominator that could put 0, it's not that I can't plug a 0 in. I mean, that might be true. This function right here, it's not that x can't be 0. It's that I would end up with a 0. Like if x was what? 3, I would end up with a 0. So 3 puts me in a position where I would not have a y value. Is that the only place where you get in trouble here? Yeah, right? Because there's no square root to get you in trouble. The way I can get in trouble with a fraction is to get a 0 on the bottom, which is when x minus 3 is 0 or when x is 3. So you could look for domains that way. But in this class, a lot of times I'm giving you a picture. And if I give you a picture of the graph, you have to look at it and be able to tell what the domain is. So on the examples that we just gave, like square root function, nothing was over here. You have to look at it and see where were there points on the graph or not points on the graph. And a lot of the situations you're going to be dealing with is finding asymptotes in places where it doesn't exist. And you have to come up with a domain from that. Okay, so if I give you a function like y equals root x, hopefully you can look at that and answer the question by saying, well, I know that I am totally fine as long as my x values are greater than or equal. That's my domain. So all I have to do is say for the domain, you could say all the real numbers except the negatives. That's a lot of writing. It's probably a little bit better just to say the x values greater than or equal to 0, or I say best. It's really not best. AP takes this and this. I like that a little bit better because to me it's a little bit simpler. And if you're writing it in interval notation, you won't accidentally make a mistake when we switch to range instead of y's, because range are y values. If you're doing intervals, you don't even have to worry about the x and the y part. But either of those is great. But remember, on this particular one, 0 is good, positives were good, all the values greater than or equal to 0. Okay? And in interval notation, do you remember, if it is equal, you put a bracket, right? And then if it's not equal, or if it goes to infinity, you put parentheses. And remember, you always list the values from least to greatest. So if I was going from negative infinity to 2, don't go 2 comma negative infinity. Go negative infinity to 2, always least to greatest from left to right. Y'all seeing that? So that's an example of domain. Another example, y equals 1 over x. Where are you going to be okay? Where are you going to not be okay? X cannot be 0. Now, here's where you got to be careful about domain and saying x can't be 0. What if I said, or what if you were talking and you said something like, man, I hate asparagus. Am I to assume that if you hate asparagus, that you love every other food on the planet? That'd be probably a poor assumption, wouldn't it? So for you to say that x can't be 0 doesn't tell me about anything else. It just tells me x can't be 0. What you really ought to say is everything, all reals, but the x can't be 0. So if you're going to say, you have to start with everything and then exclude those numbers, which again is good. It's okay, but it's not the best. The best way to do is to say either say this, all the numbers x bigger than 0, or all the numbers x smaller than 0. That's a way to go, using kind of that interval, not interval, but using an inequality notation. But again, to me, from negative infinity to 0, not counting the 0, and then from 0 to infinity, not counting the 0. Interval notation to me is just a more efficient, easy way to write all that stuff. You seeing this? Now I can do this by either eyeballing that graph, or I kind of have a visual of what the graph looks like. All right, and if I have a visual of the graph looks like, think about it. Can't you tell it's going forever left and right when you think about your picture? And didn't you have a vertical asymptote at 0? Right? So you there? So I can't include the 0, parentheses, parentheses. Are y'all with me? Okay, but don't make the mistake of going negative infinity to positive infinity, because that would not be true. It doesn't occur at that 0. So whether you have to think about the equation or the graph, that's what we're doing on domain. Now, if we do have a situation where you don't know what the graph looks like, okay, like something like this, we're actually going to get to this chapter. We're going to be looking at some rational functions. But if I asked you for the domain there, I probably wouldn't give you the function. If I did give you the function, you know what you would see in the denominator? You would see an x plus 3 down there and an x minus 1. It might not be factored, but you would see something like this. Are y'all seeing that? Now, we'd see something else on the top, but you would look at this and go, oh, look at that. What can x not be? Negative 3, because if x were negative 3, what would happen to that denominator? It's undefined. Well, look what happens at negative 3. VA. And x could also not be what? 1. Why? Because you're going to have a VA. Now, it's also possible to have a hole. We'll get to that later. But you can see a graph like this. If I had the picture of it, I could look at it and go, oh, not negative 3, not positive 1. And I could write it like this, as long as I said all reals, not those. But to me, a more efficient, better way that you will see at a math team tournament will be from negative infinity all the way through the what? And you can see my hand, I'm kind of scrolling thinking, hey, I'm hitting points on this graph. As long as I'm hitting points, I got to include it. Negative infinity, but the second I hit negative 3, there's nothing there. So from negative infinity to, open it at negative 3, because it doesn't hit. But then right on the other side of negative 3, what happens? It's getting closer and closer and closer, but never touches. So at some point, it is really close. So I don't know, negative 2.99999, whatever, but I can't say that. So I say everything but the negative 3 all the way through what? 1, because I'm listing the x values. Don't make this mistake. Don't go from negative infinity to positive infinity. We're on the intervals of domain, we're always listing the x values. Yes, it was way down there, but negative 2.99999 was there at negative 3. 0.999999 was just before the 1. And then on the other side, I'm picking up just on the other side of the 1 all the way through infinity. So even though both of these are fine right here, if you think about it, that's just to me a little bit more writing than this. And when you write it that way, you got to differentiate between domains and range by putting x's and y's in there. But writing it like this, you don't have to worry about thinking about the x and the y.
And it's never going to be a bracket because it's never going to touch.
Well, it could be a bracket, but not on this.
No.
But if it was a bracket, it'd be something like a square root function actually does hit at 0. So you'd want to include that. Or like a circle. A circle might go from negative 4 to 4, but include those points. But you're going to get practice on all of those basic functions. And if I shift the function, if as soon as I shift the function, then the domains will change. Well, the ranges or whatever as well, potentially. So are y'all with me on this? Are y'all able to look at this and see? And don't do this. I have somebody every year goes, well, I only got to like negative 3.6. And it looks like I started again at like negative 2.2. And they're putting like negative 3.6 and negative 2.2 in there. Understand, if you see a VA in there, right, you have to assume that this graph gets infinitely close without touching, right? And that's what this means. Negative 3 parentheses means I get infinitely close to negative 3 without touching. Are y'all seeing that? So don't be literal and look at the graph and say, well, it didn't get there. How am I supposed to know? Well, that's what the VA told you in there, okay? All right, and if you have a question and you're not sure, just come and ask me and I'll go, that's a vertical asymptote. More than that, but I would tell you. Okay, domain. All right. Now, I will say this. Since the beginning of the year, square roots and zeros, those aren't the only two places where the domain doesn't exist. Are there any others? In the graphs that you are dealing with right now, that are literally in front of you on your quiz, are there any pictures on there that don't go forever to the left and forever to the right? Hello? I would argue a bunch. Semicircles, your domain's limited there, right? What else? Square roots we talked about, right? Because they can't be negative underneath. There's another one.
Is it the floor and ceiling one?
Well, actually, the floor to ceiling one actually is going to have a limited range, but you can actually plug every single value in that step function, can't you? Even where it goes open circle, closed circle, there is a closed circle on every one of those situations, isn't it? And there's a line. So there's no number that I'm not allowed to plug in there. But the log function just goes like this to the right, doesn't it? Because what are you not allowed to log? Negatives or zero. And you'll notice the vertical asymptote there, doesn't it? So there are other values that you have to be careful about. So right here, if I were to say, hey, log base 2 of x minus 3, what's the domain? Without graphing it, what is important here? The domain are values that you're allowed to plug in. What? So he said it. I'm assuming that he's saying by it, he said that part has to be greater than 0. Because the rule with logs is it can't be 0, can't be negative. So if that has to be greater than the 0, what does that tell you about x? Oh, sorry. Yes, x is greater than 3. That's your domain. I don't have to graph it. Now, I could graph it, shift it 3 to the right, put that v in there, plot a couple points. What's the domain? Oh, from 3 all the way to infinity. I could do that, but that's the same thing as this. And I want you to be able to look at the graph and tell what the domain is based on either the picture of the graph or be able to look at the function and tell what the domain is based on what you know. And again, the only situations that you've had issues with are square roots, denominators, and logs to this point. But there are 2 square root functions. They go forever to the right and left, don't they? The 2 square root, the circle and the square root one, those have limited domains. You have 2 with x's in the denominator, the 1 over x, the 1 over x squared. Those have vertical asymptotes, and then the log graph. Those are the only ones that have limited domains off the top of my head, unless I'm forgetting one, that are on your basic function list. And then when we get to trig functions, 4 of the 6 have limited domains. We don't have to worry about those yet. All right. Now, somebody in this room right now is like, my head's spinning a little bit. You might need to come see me. Just come in here. I'm here at 7:30. You get 25 minutes in the morning. I can go over different problems. I can get you straight. If you're having any troubles with this, please let me know. All right, I'm shifting gears. Range. Now, range is, what does it say? If the domain is the that you can get, that you can use, that give you y's, the range is the actual y values that you get from plugging in x values in your domain. So most of the time you kind of have to understand domain to look at range, and that's a little bit different, a little bit trickier. So at this stage in your math career, what I'm going to do is probably focus more on you looking at the graph, not the equation, because it's a little bit the equation. There's a little more you have to do. So check out the range here. I am now asking myself, by the way, there's a mistake on this. You see it? Keep meaning to fix it and I'll forget. Right here, it says my range, right here, is from 3 to infinity. Bracket on the 3, because it does come down and hit 3, doesn't it? And from negative infinity to 1, bracket on the 1. You can see that, negative infinity to 1, 3 to infinity. See my mistake? Do what? Should be a y. See how easy it is when you use intervals? to just kind of get in the habit of X's, whatever. So technically this should be a Y. Please change that. And I'll try to remember to fix that. Now I put best. Either way is fine. But again, if you're using interval notation, make sure you do this. Go least to greatest. So when I'm looking at this, think, okay, it's going down forever. And by the way, as long as one part's going down forever, not every part has to. If these on the left were just stopped, but at one point it went down forever, you're going to negative infinity because there was some Y value that existed there. Doesn't matter that it's on every part. And as you're coming up, look, there are Y values of points from negative infinity all the way up to 1. But there's no Y value at 1.3. There's no Y value at 2. There's no Y value at 2.5. So I can't include any of those Y values, but I can pick up a 3, because at least one of those places was at 3, right? And I can take that 3 all the way up to positive infinity. So it doesn't matter that they're all doing that. Does not matter. As long as one of them's going up forever, you're okay. Or you could just kind of think about, if you put your arm and just slid it up and down, where am I hitting points? I'm hitting points everywhere from negative infinity to 1, and I'm hitting points from 3 to infinity. Negative infinity to 1, 3 to infinity, but I got to bracket them, right? Yes? Okay. So that's range. But if you think about some of the other graphs, think about this graph. What's the range on something like that? If you think about it, start at the bottom. How low does this go? Negative infinity? How high does it come? It goes to positive infinity, place where the Y value doesn't exist. The x-axis, which is Y equals 0. So Y has negative infinity, negative 100, negative 5, negative 3, negative 1, negative half, negative 0.1, but nothing at Y equals 0. So nothing there. But on the other side of 0, it does have something, and then it rises all the way to positive infinity from there. Y'all seeing that? And if it's shifted or whatever, so be it. But you've got to be able to look at them and see that. And just think, as I'm coming up, think, if I'm bringing up a horizontal line like that, where am I hitting values? And as long as I'm hitting values, you include it. But if I ever miss something, you have to not include it. And I can't exist at 0. All right. Next thing, symmetry. There are lots of symmetries out there. There's x-axis symmetry. There's y-origin symmetry. We're not going to talk a lot about x-axis symmetry because at least in this section, because if something is symmetric about the x-axis, and I'll just kind of draw a sketch of this. Like here's something that might be symmetric about the x-axis, right? You can see that symmetry, like if the x-axis was a mirror, you can see a mirror image of that. Well, if you have x-axis symmetry, it ends up not being a function. And since we're dealing with some of the basic functions, we're not going to see any of that in anything we do here. But if you do have y-axis symmetry, the way you can check for y-axis symmetry, this is an example right here of the x equals y squared graph. Is if I ever replace my y with a negative y, this is a little trick. If I put negative y in its place and then simplify it, if I get the exact same thing I began with, then it has x-axis symmetry. So even if it was a really ugly looking problem, like if I gave you something that you might have no idea and I said, what does that graph look like? You're like, I don't know. I'm like, well, can you tell me if it is x-axis symmetry or y-axis symmetry or origin symmetry? You could come in here and replace that y with a negative y. And when you simplify, what does the 2 and the 4 do? Makes it back to where it was, right? So plugging the negative y in here is going to look exactly the same as the original. This actually has x-axis symmetry. And I know that because of this little check. I know that I asked this in this class, but I know I ask it in my pre-cal class, and I know AP asks it occasionally too. They want you to understand it. Now, here are the two symmetries we will talk a lot about because these show up with functions. And a lot of our basic functions will have these symmetries until you shift them. And when you shift them, most of the time your symmetry will disappear. Not always, but most of the time. So check this out. What if, let's talk about y-axis symmetry first. So y-axis symmetry is unique in that y-axis symmetry, like we said with x-axis symmetry, would reflect over the y-axis. We have a lot of examples like that. The absolute value function has y-axis symmetry. The what else? Parabola function, y-axis symmetry, right? What else? What else?
Absolute value.
Absolute value, y equals x squared. Bird function. Volcano function. I think of at least one more off the top of my head. Semicircle function. Right? All of these have y-axis symmetry. And the thing about y-axis symmetry, if it has y-axis symmetry, this is important for you to know, huge in AP. Not huge in AP, it shouldn't be huge in AP, but it is huge in AP. If it has y-axis symmetry, it will always be what we call an even function. We're going to talk about even functions more and more this year, but if it has y-axis symmetry, always an even function. Always. Not part of the time, always. Okay? And we'll talk about, again, we'll talk about it even a little bit later. Cosine, we don't know what cosine is just yet, or maybe you do know what the ratio means, but the cosine function looks, you can see it has y-axis symmetry as well. Although you don't need to know that. Oh, and how do you check to see if it has y-axis symmetry? Well, obviously, if it has y-axis symmetry, well, not obviously, it could be a circle. Circles have y-axis symmetry. All right, if they're located like at the origin or like right on here, they can have y-axis symmetry, but they wouldn't be functions. That's okay. But if it has y-axis symmetry, you could use that little check that we did with symmetry, but switch it. So for y-axis symmetry, if you replace any x with a negative x and then simplify it, you get the exact same thing you started with. Can you see that here? I put a negative x in there and square it, I'm back to x squared. If I put a negative x in there, what's absolute value do always anyway? Makes it positive, there's your positive absolute value of x. You don't know that, but cosine of negative x is also cosine of x, you'll learn that later. But those are even functions when they have this y-axis symmetry. And then I shift it, guys. What happens if I shift this to the right? And now it's this. Does it still have y-axis symmetry? This is still the y-axis, right? Symmetry's gone, isn't it? Don't go, but the new y-axis, when we say y-axis, we mean the original, the official y-axis. So as soon as I shift it left or right, your symmetries are gone. Now, what if I shifted it up? If I shift this one up, does it still have y-axis symmetry? Okay, so it's possible to still keep a symmetry after a shift, but most of the time your shifts are going to eliminate your symmetry. Y-axis symmetry, always linked with even functions. All right, origin symmetry. Now, origin symmetry is not a linear symmetry. It is not like, I don't know if y'all ever did this, but like fourth grade art. Take the piece of paper and you put like paint on one side and you fold the paper and it makes a butterfly or whatever. Do y'all ever do this? Okay, yeah. Well, that's symmetry about the fold. That's a linear symmetry that you did, all right? And that's what y-axis symmetry is basically saying. If you had something on one side and you folded it over and it was on the other, you would see it on both sides like that. An origin symmetry is a little different. Origin symmetry is a point symmetry. So to visualize origin symmetry, it's kind of like this. Say you have a graph, right? And I put a nail at the origin. Like, so I had a graph on a big piece of poster board and I put it up here and I put a nail on the origin. I nailed it into the wall here. Okay. So it's just pivoting on that one nail. If I can take my poster and rotate it 180 degrees, so take the top part, move it down to the bottom part. If I can do that and it looks exactly the same, if I do that, it looks exactly the same, it has origin symmetry. And if it has origin symmetry, it's considered an odd function. We'll talk more about odd functions along with even functions later. Graphs that we have on our basic function sheet on the quiz. Which graphs, if I nail at the origin and spin 180, look exactly the same? List them. Talk to me. Come on.
Y equals x to the third.
Y equals x to the third. You skipped one though, but definitely right. Y equals x. If I name, still looks like y equals x cubed. What else? Think about the pictures.
Oh, y equals 1 over x.
Y equals 1 over x, which is the cube root function. What else? Nail it at the origin, spin it 180. Now the semicircle, if I spin it 180, it looks like an upside down semicircle. Did that look exactly the same? It's okay. What else? 1 over x. Remember the one that looks like this, the broken band director or whatever? If I spin that 180, that bottom part here ends up on the top, and the top part here ends up down on the bottom. Are there any other ones off the top of my head? I don't think there are any, but there's one people confuse. The step function. At first glance, if I rotate it, it still has steps, but what's different? Open circles, instead of being on the right, are now on the left and vice versa, right? So it did change some, can't count that. Y'all seeing this? Now hopefully you'll link in your head right now. Y-axis symmetry, even function. Origin symmetry, odd functions. And then when you learn the definition of even or odd, you'll be able to tell about symmetry from your even and odd definition without having to graph it. And that's an important connect. If you link in your brain permanently, y-axis symmetry goes with even functions, origin symmetry goes with odd functions, then when you don't know what the graph looks like, you could still check the even and odd function definition to find out about the symmetry, because they always go hand in hand. Oh, another thing, for origin symmetry, you know the little trick for x-axis symmetry, you can for y, see if it's the same. And then for y-axis symmetry, you can plug in negative x for x and see if it's the same. Well, for origin symmetry, you can plug in negative x for x and negative y for y and see if it's the same. So even when the functions get really ugly and you don't know what they look like, that is a check that you could do. And that little check that I'm showing you is essentially checking the even and oddness of the function. All right, but it allows you to do it even when they're not functions. And it's a nice little thing to have in your back pocket. Okay, last couple things, roots. What's the root? Another name for it. I've used it a bunch simultaneously with other stuff. Okay, so one definition of a root would be an x-intercept, but that would only be true if the root was real. Because the root doesn't cross the x-axis. But if it's real, it would be an x-intercept. But a root is a zero or a solution. And a zero, it means when y is 0, it's the x value you get. So if I ask you to calculate the roots and you have a picture of the graph, if I asked you to calculate the real roots and there's a picture of the graph, you could just look down and see where it crosses. And if it crosses on a whole number, awesome, write it down. Now, if it doesn't cross on a whole number and you're not quite sure if it's 1/2 or 1/3 or 2/3, if you're not sure, you could always plug what in for the y? 0 in for y and just solve. And that's what I would encourage you to do. For instance, what if I gave you a function like this? Now, there's all kinds of stuff going on in this function, right? Function up 5, and it's one of these graphs like this, and it's got a stretch on it. But I probably don't know exactly where it crosses the x-axis. But that's okay, because I can just plug in 0 for y, move the -5 over, cross multiply. You could multiply everything by an x minus 2 if that makes you happy, and use the algebra you already know and solve for that x value. And that would be your root. Now, occasionally, you get a graph that looks like this. We've talked about, are there roots of this function? Yes, they're just not real. Now, if I ask you for the x-intercepts, what can you say here? There aren't any. But if I ask you for the roots, Roots, by definition, means zeros, where y is 0. So even if you have a graph that doesn't cross, there can still be imaginary roots, and you'd have to go find them, which is not a graph like this. Maybe you have something like clearly over 2, up 1, going up, right? Can't I still replace that with the 0 and start the solving process, right? Subtract the 1, multiply both sides by and then add the 2 over. So I can always find the roots, whether they're imaginary or whether they're real. But if I ask you the question x-intercepts, in a situation like this, if I said x-intercepts, you would just toss those and say there aren't any. But if I ask you roots, make sure, okay? And a lot of times I will just say, determine the function's real. And if I say real roots, and you know it doesn't cross the x-axis, you don't have to write anything. Y'all seeing that? Okay, so of these basic functions, and this is the chart I told you to ignore. No, this is not. This is a different one. But on this one, I just want to walk you through a couple of these. We've got time. So let's look at these. And we're talking about these basic functions. And I hope they're burned into your brain so you can visualize them. Tell me the of the y equals x graph. What's the domain? All reals. You can write that funny R, which by the way looks something like this. It's like an R with 2 bars. Or you can write something like negative infinity to infinity. And I know that because you can see it going forever to the left and forever to the right. I know it looks diagonal, but it is moving left and right, isn't it? Okay, range. Also all reals. Again, negative infinity to positive infinity. Y-axis or origin symmetry. Origin, because if I nail it at the origin and spin it, right, still looks the same. If it doesn't have those, you can say neither, or you can say no symmetry. Now, no symmetry doesn't necessarily mean it doesn't have some kind, but it has none of the kinds we're talking about. Don't write if I ask you about symmetry. Well, it has symmetry about the line x equals 3. Don't tell me that. Or it has a symmetry about the line y equals 1. Don't tell me that. Now, on my test, it's going to say, is it have y-axis symmetry, origin symmetry, or neither? And then is it even, odd, or neither?
Odd.
How do I know it's odd?
Because it has origin symmetry.
Origins are always odd, right? Which hopefully is easy to remember with the O's. And then determine the function's roots, real ones. Where does this one cross the x-axis? At 0. The y equals x squared graph, domain. All reals? Now, if you're looking at that and going, Mr. Hurd, it's hard for me to buy that because it's starting to go so steep. Does a parabola ever go perfectly straight up? No. And think about it, if it did, that would mean that you could, like, say it started to go straight up at x equals 1,000,000. That would mean you can't plug in 1,000,001. But you can plug in 1,000,001, can't you? Keep plugging in numbers. So don't be confused about stuff like that in your head. Look at it. Is there anything keeping you from plugging an x in there? No, you don't get imaginaries. There's no radical. You don't get undefined. There's no denominator. There's no log. There's nothing keeping you from plugging stuff in. It's got to be all reals. Now, what about range? It goes up forever, clearly, right? Prowess? But what does it do when it comes down? It stops at, does it include 0?
Yes.
Yeah, so bracket the 0, go to infinity. Now, if you want to say all y values greater than or equal to 0, you can. But I see a lot of people who write it like that use x, like I accidentally did. It's easy to do that, but you won't run into that if you just use the interval notation. What kind of symmetry does it have? Y-axis, which means it has to be an even function. So 2 for 1 right there. And does it have real? Does it cross or touch the x-axis? The parabola? Touches where? At the origin, so where x is 0. And again, if you were confused and didn't know that, couldn't you take the y equals x squared graph and plug in 0 for y and just solve? You get x to 0, right? And as soon as I start shifting and moving these, your roots are going to change. You're going to go from one root to having two roots or imaginary roots, all kinds of things. Just to shake things up, jump down to the square root of x function. So I'm doing this square root of x. What is the domain? Square root of x. Bracket on the 0, because I can plug a 0 in there all the way through infinity. And isn't that basically saying everything except negatives? What's the range? It came down as low as 0. It did hit 0 on the y, because it does include the point 0, 0, and it went up forever. Oh, but it kind of flattens out, though, doesn't it? Isn't there a point when it flattens out completely? No, right? Because if it flattened out completely, that would mean that no matter what I plug in for x, I don't get a bigger y value. But that can't be true, right? Plug in bigger and bigger numbers, I get bigger and bigger numbers. This thing is always rising, even though it does appear to flatten out a little bit more. Start getting smaller, it's still growing. Y-axis or origin or neither? Neither symmetry, right? This is neither even nor odd. I mean, it has no symmetry, so no symmetry. And then neither even nor odd. Does that have any roots? It does hit at 0. And again, that is bound to change as soon as I start shifting and reflecting and stuff. What about jump down to? So that's the volcano graph. So talk to me about domain with the volcano graph. So I definitely go negative infinity because it's heading left, right? But then the second it hits x equals 0, what do you see there? A vertical asymptote? Well, nothing's at an asymptote. So 0. So that's saying it gets closer and closer to 0 and never touches. That's what an asymptote does. And then what? 0 on the other side to infinity. And then how do I join these? I should put a union, but in AP Cal, they get sloppy and they put commas. But a union is better, but comma's fine. And then range. Because it never touches, does it? It gets really close to 0, but it never touches it, but it does go up forever. 0 to infinity. What's that next blank? Is that symmetry? So what kind of symmetry does it have? Y-axis. And then what does that mean? So what? Must be even. Because remember, origin, odd, y-axis even. And then the last thing, what are the roots? Now, they're not any on this one, but as soon as I shift it down, what happens? It's going to cross a couple times, isn't it? So remember, don't just memorize this chart. These are the basic functions. All this changes as soon as I change something about the function. Okay, so right here I would say there are none, no roots. So for example, on this next one, what if I made this y equals 2 over x minus squared plus 4? Now think about that graph. What would that look like? To the right one, up 4, and there's a bit of a stretch on it, right? But still pretty much a volcano graph. So if I did this, now what's my domain? Now it would be what? Think left or right. Negative infinity all the way through what? That's, if I go up 4, that's like a range thinking, isn't it? Negative infinity through, I get closer and closer to 1, but I never touch it. Then 1 through infinity. Are y'all seeing that? Now what about range? I don't come down and hit 0 anymore. What do? I come down and hit almost 4. So 4 to infinity. And if that had been reflected, I'd be what? Negative infinity to 4. Y'all see the difference? And then what kind of symmetry?
Still y-axis.
I got nothing. Now, it's symmetric about the line x equals 1, but that won't be the question, right? The original y-axis is this. And look at it. Is that symmetric about this? No, there's too much chunk right here. So no y-axis, neither. Say neither. And then if it's neither x or y-axis symmetry, is it even rod? No, neither. Does it have roots? Well, I can look at it and see that it has no real roots. Now this said real roots, so I can say none. All right, and again, this is not, don't put this in here. This is not that. This is if I were putting this in there. But do you see how all of this changes? That makes shifts and reflections. So please, I didn't give you this to memorize. People go home and memorize this and then just miss easy questions. I gave it so that you would kind of get some practice with some things that are a little bit more simple to think about. But if I make the graph more complex, do a little sketch to get a visual of it, and then walk through what you know. You seeing this? About the log graph. Down here at the bottom. Domain. There's two ways you could do this. You can think about the graph. You can also look at it. What do you know about logs? You can only log what? So this number x has to be what? Positive. You could say that. Now, if I shift it, it might be that x minus 2 has to be positive. Or that 2x minus 4 has to be positive. But in this case, that x has to be positive. You can write that. I would probably write from 0 to infinity. Plus, what does the graph look like? Doesn't it look like this? Can't you see that it goes, never hits 0, gets pretty close, but runs off to the right? What's the range? Negative infinity to positive infinity. Oh man, doesn't it eventually flatten out? No, I keep logging bigger numbers, I get bigger y values. So negative infinity to positive infinity are all real. What kind of symmetry? Neither. Is it even a rod then? Nope. Does it have any roots? Oh yeah, it does. So how do I do that? I take this function, I put 0 in for y. How do you solve that function? To get x by itself, what would you have to do? So exponentiate, remember this? You exponentiate both sides. What happens with log 2 of x? Oh, on x is 1. Oh, I kind of knew that though if I graphed it. Are you seeing all this? Right now, some of you are like, man, this is child's play. And some of you are going, holy crap. If you're a holy crap, come see me about it and let me straighten you out. Because I guarantee you, if we do enough of these, it'll click. And you'll be in great shape on that part of your test.
Is there a test still this week?
No, did I give you a new assignment sheet?
No.
I did not?
I didn't get one.
Last Friday you did.
Oh, I didn't give you one today.
No.
Thank you for saying that. I got a new one. And I updated everything in Schoology, so just follow this. Yeah, you can keep it because it's same as that. So your test will be Tuesday, not the Friday of this week, which was on your original sheet. So just throw out all the other steps. Schoology test is going to be in good shape.
Oh, no. Absolutely.
Do it next year.
I learned it. You didn't have it.
Y'all have a good one.
I did. You're
Those are so fun.
For the first test.
I'm not in for it.
It's not good, and I'm just not good, so.